We're going to start to look at thermochemical equations, and in order to understand what is happening here and how these things work, we first need to look at some of the terms and think about how energy can be released or utilized by chemical reactions. So the first kind of term we're going to look at here is this energy term. And when we see this delta value, this is a Greek symbol delta. It actually means change. So we're looking from the change after the chemical reaction, what the energy was before and after. So this is the change in energy that's happening during the chemical reaction. And then we are going to look at heat, which is Q, plus work. So we are going to be looking at this energy in regards to how much heat it produces and how much work it is doing. Some terms we need to look at: when this Q is a positive value, it means that the system or the chemicals that we're looking at are absorbing heat. Otherwise, if Q is negative, it means that chemical reaction released heat. If work is positive, work was done on the system, and when work is negative, work was done by the system. So work done on a system usually means it's being compressed in some way. It's changing to a smaller volume. When work is being done by the system, it's expanding and the volume of the chemicals are getting larger. Some terms that we need to look at and understand for when this overall change in energy increases, so we're adding either work or heat, a combination of the two, whatever that happens to be, when we add these together, when that delta E is positive, this is an endothermic reaction. When it's negative, we call it an exothermic reaction. So when there's an overall release of energy, it's exothermic. When it's an overall intake of energy, then it's endothermic. So an example of an endothermic reaction we're going to look at as an example of photosynthesis. So when this flower, for example, is going to take the sunlight, the energy from the sun, it's going to take carbon dioxide and water from the environment and use that to make sugar molecules. So this is actually, we're storing that sugar for energy for later. It's kind of the same thing, charging a battery, we're storing energy, so it's taking on energy, so it's going to be endothermic. So this change, the final energy level after it's taken on that sunlight is higher than the initial, so this overall delta E is a positive value. Another way to look at delta E, or the change in energy, is by looking at a fully charged battery. So these would be an example of where there is fully charged, and then when we go to a dead battery, discharged, this delta E value is going to have an overall negative value. So this is an exothermic reaction. And two things can happen, right? We can have heat being released. If I short circuit this battery, all of the energy flows through that metal. We're going to heat the metal up and we'll discharge the energy and it'll come out as heat. We could also hook this up to a fan, for example, and do some work. We can move that fan blade, and that's work energy, and then it'll be eventually discharged. Usually work isn't going to be 100% efficient. For example, you can see here heat is still being put off. So there's still some Q and W. There's heat transfer and work being done. In this example, it's only heat. So it's really hard to get really 100% efficient reactions that can occur that will produce only work. But that's why LED lights are replacing typical incandescent lights, where you have kind of that coil. Because I don't know if you've noticed, if you've tried to change one of those light bulbs, they end up being really hot if they have been on recently, where the LED bulbs are more efficient, so they put out less heat. So it doesn't matter how this delta E changes, the end result is still the same. You still have the same initial amount of energy in the fully charged battery, and in the end, that battery is dead. The energy has been released either through heat or through work and heat, or through just work if you have a very efficient motor, for example. But so the end is still a dead battery, and it's independent of the pathway. So take a look at this question. So we're basically looking at playing with a Batmobile that runs on a battery, and the toy will actually read out how much energy is in there in joules, the unit joules for energy. Right now it's sitting at 2,000 joules out of a total of what it could have is 6,210. So what's the change in energy after you charge that battery? So take a shot at this and add that into our Blackboard discussion space. Now I'm going to introduce you to another term called enthalpy. We have been discussing this as energy, which, that term I'm assuming is more common with what you would understand as energy. And when we look at this, we have to take into consideration work and heat. The problem is that this becomes more difficult to measure the work being done by a system without more complicated setups like bomb calorimeters. These are big calorimeters that are in water, and they are enclosed in a really strong container with the kind of bomb here in the middle, which is also made of metal. So we're not going to allow this to do any work, basically by keeping the volume constant of our reaction environment. So we'll put the components in here, we'll ignite them, we'll burn them, and then we look for the heat transfer into our system, and work can't be done if the volume doesn't change. So this is more difficult to do and doesn't always work really well for some of the kind of reactions we're going to use. So instead, we're going to use this term called enthalpy, which is very similar to work. It allows us to solve the same problems and understand the same kind of system. So here's the definition of enthalpy. It's the energy of a system plus the pressure and volume. So what this also does, it's called the state function. It allows us to know and do this all over the world essentially, and then know what kind of energy or heat is going to be released from a system under standard conditions. Because then we know what the pressure is. So I could do this on the moon, I could do this on Earth, I could do this on a mountain on Earth, right, where the pressures might change, because I can keep track of that work that's being done. So this allows us to better understand what's happening in our system. So at a constant pressure, we would have something like this. The change in enthalpy is equal to the change in energy plus the pressure times the change in the volume. The pressure obviously has to be constant here. Again, this allows us to bring these state functions together, which we can get rid of the concerns of that pressure and volume change, and we can do these under standard conditions, which is typically 1 mole of the compound we're looking at, 25 degrees Celsius, and 1 atmosphere of pressure. So those are some of the standard states at which we would look at this. This delta H value with that little degree symbol, that is what we say is the enthalpy of that system. Under standard conditions is what that little degree sign means. So this delta H we use the same way when we were talking about the energy. When we have a delta H that's positive, we say it's an endothermic reaction, which means that the system or the chemicals that we're studying are absorbing energy from the surroundings. And if it's exothermic, it's going to be releasing energy into its surroundings. A lot of different chemical reactions that are occurring in chemistry, especially biochemistry and biology, they're actually happening in liquids. So, which is nice because liquids don't typically change a lot. Their volume doesn't expand or contract very much, not as much obviously as a gas might. So if we take this delta V out of the reaction, if we're talking about solids and liquids, if those aren't changing, their volumes don't change, then our enthalpy is essentially the same as our delta E. So now we're going to talk about how this is working in our chemical reactions. And typically when we're reacting to different molecules, something that's going to happen is we have to have a bond breaking, and then we have new bonds reforming. So there's a certain amount of potential energy that's stored in these chemical bonds, and it's based off of how far these electrons that are being shared are attracted or how close they are to the protons in the nucleus. So remember we talked about we have protons in the nucleus, we have an electron cloud. So if we have two hydrogen atoms here, we have a proton, and two electrons being shared. When we have to look at how these are shared, the further they are away, it's kind of like walking up a hill with a bowling ball, right? The further away, the further up the hill I climb, the more potential energy it has. And we know that gravity is going to want to bring it back down to the bottom. So the higher up the hill I climb, the further that potential is, and we have more space for that to move, and it would have higher potential energy. As we get bigger and bigger atoms and those electrons are further and further away from the proton, the closer they can get, the more stable that system is. The further away they are, the more potential they have. So this is how we kind of will look at breaking and reforming new bonds. I mean, when we form bonds, we get these electrons, the electron clouds are closer to more positive charge. So we actually will release energy in this state because we're getting those electrons closer to more positive bonds. When we break bonds, that actually requires us to pull those apart, and we have to put energy in that system, just like we'd have to put energy into walking a bowling ball up a hill. When we're looking at different types of bonds have different strengths, so we might need more energy to break some bonds apart, and then when some other bonds come together, they might release more energy or release less energy depending on how much potential was there. So again, energy is needed to break bonds, and then different bonds have different amounts of energy. In this instance, if we have methane gas plus oxygen gas, so we have 1 part methane, 2 parts molecular oxygen, it reacts to form 1 part carbon dioxide and 2 parts water, which produces heat. So this would be an exothermic reaction because heat is a product and heat is released. We always need a little bit of energy to break the initial bonds. So if we're looking at, these are reaction energy diagrams I'm going to show you here. If we have a certain amount of energy, we're looking at energy here, and then the reaction progression on the y-axis. We'll start out with a certain amount of energy. We always have to put a little bit of energy in to, these will help to break bonds. So we're going to break these bonds, right? These are going to break apart. And we're going to break these bonds here between the carbon and the hydrogen. So that first part is going to break the bonds. And then here what's going to happen is the energy is going to fall off. And we're going to have an overall reduction in the energy that accounts for, so then this is after we reform new bonds. And this will be the final energy state of our products. So this is the idea of why actually we release heat. These compounds here, these new bonds between especially the oxygen and the hydrogen, these are new water molecules. They have, these methane and oxygen have weaker bonds, and the carbon dioxide and the water have much stronger bonds. So those weaker bonds and stronger bonds were now a more stable compound, and that overall chemical reaction, we can see, will form a lower, more stable compound, but that released heat during this process. So this is, again, that same example of an exothermic reaction where we're breaking these bonds, we're going to reform these bonds, and it releases energy. So this is a negative heat, this is a negative value, this would be an exothermic reaction. Looking at an endothermic reaction, this is like what photosynthesis would be. We would take carbon dioxide. A plant takes carbon dioxide and water out of the environment. It uses solar energy to then glue these, re-break these down, re-put them together into sugar compounds, and then we also release oxygen. So it's kind of doing that reverse. It's using this energy to make this molecule and oxygen. So this is where we'd have to put energy in, this solar energy in, to the reaction, so it is endothermic. All right, so I want you to think about this in terms and define which of these is an endothermic process. And why do you think each of these might be an endothermic process? And remember, I want you to think about if bonds are being formed overall, then we're going to actually be releasing energy. If we have to break bonds, then we'll have to put in energy. So kind of look through these and decide if we're breaking bonds, making bonds, or if you think that it makes sense that we'd get energy out or have to put in energy for these things to happen. Now I'd like to start talking about thermochemical equations and our enthalpy, or change in enthalpy chemical reaction. So under standard conditions, typically again 25 degrees Celsius, 1 atmosphere of pressure, and where we are talking about 1 mole of our compound. So I'll talk about that in a second here as well. These are standard heats of reaction. So you should be able to repeat this anywhere where these conditions are upheld, and then we'll get the same amount of heat out of our system, out of the chemical reaction every time. So here's an example. We're looking at 1. So when I talk about 1 standard condition, that's where this would be a 1 mole of nitrogen gas. And we'd have 3 moles of hydrogen gas. We'll react to form 2 moles of ammonia gas, and it'll release 92.38 kilojoules of energy. So our enthalpy, our change, our delta H, 92.38 kilojoules. This is a negative, so that means it's releasing that amount of energy. Again, the coefficients here under standard conditions, this has to be a 1 here, so it's 1 mole. This has to be a 3 moles because we need to have, this is a balanced equation. We have to have a balanced equation, and this is how that example would work. So we're talking about 1 mole of this, 3 moles of that, 2 moles of that will give us this. So we can start using these as different conversion factors. So we have 1 mole of N2 is equal to 3 moles of H2. We have 1 mole of N2 will give us 92.38 kilojoules of energy, right? We'll release negative 92.38 kilojoules. 3 moles of H2 will release 92.38 kilojoules of energy. So these are all things that now we can use as conversion factors when we're trying to solve problems using stoichiometry and thermochemical reactions with delta H values. For thermochemical equations, we are going to include heat now. But the difference is we don't necessarily put this heat on the left side. We're always going to put it on the right. And we'll write the delta H equals a positive value if it's an endothermic reaction, and it'll be written on the right side as a negative value if it's an exothermic reaction. So that tells us that if it's a positive or negative, tells us if we have to put energy in or if it releases energy. Here's an example of a thermochemical word problem equation. And so when we're looking at reacting N2 and H2 to form ammonia at 25 degrees Celsius, 1 atmosphere, 92.38 kilojoules are released. So that delta H is a negative 92.38 kilojoules. Is this endothermic or exothermic? So I told you, remember, if this is a negative value on the last slide, that's going to be exothermic reaction. So if we have heat is required, that's going to be a positive delta H. And if we release heat, that'll be a negative. So this would be an exothermic reaction. Some rules of writing these thermochemical equations. Again, writing the delta H value on the right side with a negative, this is exothermic. Some other things, another ways that you can treat this. So this is under standard conditions, but we can change this. We maybe don't want to run this under standard conditions. Maybe we want to use more or less nitrogen, or we want to scale this up or scale this down. We can do that by simply multiplying this whole entire equation by certain amounts of values, right? So if we want, this is the standard condition on the top, but let's say we want 5 times more. So we'd use 5 moles of nitrogen and 15 of the hydrogen, and then we get 10 moles of the ammonia. And then we also have to multiply this value by 5 as well, which would be negative 461.9. So we multiply this out throughout all of the components of that reaction. Maybe we don't want 5 moles, we don't want more, we want less, we want half as much. So we use a half a mole of N2, we use 1.5 moles of the hydrogen gas, we get 1 mole of ammonia, and we'd also have to divide this amount of energy by half as well, because we'd reduce the amount that we're reacting. So just some ways that we can manage and manipulate these equations to get what we're actually using. Delta H values under different states, if we have a liquid versus a gas. So we have methane and oxygen react to form carbon dioxide and water. These are both the same besides the state here, the liquid versus the gas. And what's happening if we have liquid water versus gas water, if I have gas water, it means that it's floating around in the environment and they are kind of independent of each other in the gas state. When these condense, that means that the water is going to condense and it's going to be kind of stuck to itself. And that's what makes it become liquid, is that there's a connectivity to it. It condenses and it pools together and it comes out of the environment. So when that happens, that liquid gas or that liquid water versus gas water, we're going to actually create new bonds there. When we form bonds, we know that that has to release some energy. And that's directly the difference here between 802 and 890. It's that extra approximately 90 kilojoules is that energy that's being released as that condenses and forms new liquid-liquid bonds. And that's the energy that's being released. So it's equivalent to the energy on the opposite side if we go backwards, right? So that we have to take energy out if we're going from liquid to gas, that energy to form that gas to kind of essentially vaporize it or boil it, that's the energy difference as well. Just to look at some of these different types of word problems and how we can use these thermochemical equations to understand what's happening and use it in maybe the lab space. If we have the chemical reaction with methane, and now we're looking at chlorine gas, we're going to make CCl4 gas and 4 units of HCl gas. That reacts to form and release 434 kilojoules of energy per mole of CH4. So what energy change occurs if I have 1.2 moles of methane? And to set this up, I'm going to take my 1.2 moles of methane and I'm going to multiply by the negative 434 kilojoules per 1 mole of methane. And I can cancel those units out and multiply that negative 434 times 1.2 and I get 520.8 kilojoules of energy released. It's going to be a negative value, right, because I have the negative here. And now I can use that idea to understand how much, if I'm changing the amount, how much more energy I'm getting out based off of this conversion factor that's part of the thermochemical equation. Another useful feature for thermochemical equations, if we have a forward reaction, so I'm making methane and oxygen, generating carbon dioxide and water, I can actually spin these around and I can start with the products, carbon dioxide and water, make methane and oxygen, and what happens to the delta H value is it just gets to be the opposite value. So negative 802 kilojoules for the forward reaction, the reverse is a positive value. So this is kind of the idea of the state functions as well. It doesn't matter how you get there. The energy associated with this compound is the same regardless of how you get to this state. And so that is another reversing chemical equations, just changes that from a positive to a negative. Because we'd have to put, just like how we had to with plants, photosynthesis, we had to put energy in to make these new molecules. And again, so we're going to go through an example of this, but we can have chemical reactions that do one step with the products versus multiple steps. And it doesn't matter, again, how we get there. Those products have the same amount of energy, and to get there, it's going to cost us the same amount of energy to get there. So the enthalpy is independent of the pathway. It doesn't matter. And so I'm going to show you some examples of what I mean by that. Here's a single step pathway where we have solid carbon, and we're going to react it with oxygen gas. That's going to react to form carbon dioxide, and it's going to release about almost 400 kilojoules of energy. So that's one step. We can go from just these two, we add them together, we get this compound. Now I'm going to do two steps. If I have a two-step pathway, for example, maybe we just take carbon. It's going to react with a half a mole of oxygen to form carbon monoxide, and we're going to release about 110 kilojoules of energy. The next step, we're going to take this carbon monoxide right here as a new reactant. We're going to react it with another half a mole of oxygen gas, and then that's going to form carbon dioxide, and then we release 283 kilojoules of energy. So I can add these different reactions together. I can basically take the things on both sides of the arrow here, and if they're the same, we can cancel them out. So I can take that carbon dioxide out, and we can add things on either side. So I'm going to add the carbon on the left side, and I'm going to add my half a mole to give me 1 mole of oxygen, and then the CO2 is there, and then we're going to add together our heats of enthalpy, and to get a total of negative 393.5 kilojoules. So notice that this value is the same now as this value. So it doesn't matter how we get there if it's multiple steps. We're still going to, in the end, have to use or there will be released the same amount of energy as a single step. I want you to take a second to look at this and just kind of the same idea. We have a single pathway step up above, pathway A, and then we have a multi-pathway step for pathway B. So the first step is nitrogen to oxygen. We make nitrogen monoxide. We take that compound, and then we react it with more oxygen, and then we get nitrogen dioxide. So I want you to look at this and think about what I had talked about on the last slide. Decide what this step 2 for pathway B, what is the energy that's going to be involved here for the enthalpy reaction, and then what is the overall net reaction for pathway B. So make sure that you understand that, post that in our Blackboard space. In that last example, both pathway A and pathway B, in the end, overall, were the same exact reaction. We have N2 gas, 2O2 gas, react to form 2NO2 gas. And that is going to take on 68 kilojoules of energy. So in order to break these bonds, and then even the energy that's released when these are reformed, it's still that overall is requiring 68 kilojoules of energy. We can't measure this delta H directly, perhaps, for a certain chemical reaction, but we can add different chemical reactions together to find some of them to know what that overall delta H might be. So this is the idea of Hess's law, where we look at for any reaction that can be written into different steps, like we did in pathway B here, the value for the delta H reactions, the sum of them equals the value of that total, will be the sum of the total of the individual steps. This allows us to determine different types of heats of reaction for different reactions that we can't necessarily measure directly. We can do that separately through adding these groups together. So just to reiterate this Hess's law, if we have this pathway that we were looking at earlier with carbon and oxygen and carbon dioxide, we can release 393.5 kilojoules, so negative 393.5 kilojoules. We can't maybe do this directly, but we can do some other reactions where we go to carbon monoxide and then carbon monoxide to carbon dioxide, and we can add those two up to get the same resulting reaction. So this just gives us a name. This is Hess's law. to the things that we were doing earlier and working through these different thermochemical reactions. Just to be able to visualize this idea as well, it's kind of helpful. We have these enthalpy diagrams that show you kind of where these elements are in terms of their potential energy before and after a chemical reaction. So if we look at these enthalpy diagrams, we can see that carbon and oxygen have a high potential. So it's kind of up. You can kind of think of this as maybe gravity or how far away from the ground you are. So these are up high. And when we do that chemical reaction, we can use that first reaction, pathway A, where it just directly goes to carbon dioxide. We see a large fall. And this corresponds to, you'll notice also the arrows are pointing down. That means that these are the reactants and this is the product. And that's going to release 393.5 kilojoules of energy. So we have a high potential. We go down here to a lower potential. To get from top to bottom, we're going to release energy. We can also do this in the stepwise fashion, where we have this carbon and oxygen make carbon monoxide. We take some more carbon monoxide and oxygen, and then we can make the carbon dioxide. This is a two-step process, and we get little chunks of that energy for each little pathway for how far we fall down that energy diagram. So this is just a good way to a graphical description of this law and how this works, where the vertical axis is the enthalpy scale and the horizontal line tells us where these different states of the reaction are, or how far along that pathway they are. And you'll notice again that when we add these 110 and 283 together, we get that total. The total should be the same. One other thing I want to note on here is you'll notice the arrows point down right now. We can point the arrows up. You can switch the chemical reaction. The difference then is, again, that's delta H value. Instead of being negative, if we turn this red arrow upside down and it's pointing up, we're going to have add 393.5 kilojoules of energy to go from carbon dioxide to solid carbon and oxygen. So we have to put energy into the system if we want to go up. So you can do that. You just need to swap the positive to a negative or the negative to a positive if you're going the opposite direction. So I want you to look at this and I want you to decide, I want you to write out what is the thermochemical equation for this reaction. What would the full chemical equation be? And so some things you'll have to notice. What are the reactants? What are the products? How do you know? If you're not sure, maybe rewind and watch that last description of these diagrams and how we do this. So I want you to do the full net thermochemical equation and post that in our Blackboard space. If you have questions, please ask. Once you have the full thermochemical equation written out, next, this is a different step. I want you to decide what is the enthalpy change for step 2. So what is the delta H for this dotted blue line here? What is that going to be? So answer that, post that in our Blackboard space, and then ask questions if you're not sure how to work this problem. In this next part, we're going to discuss the manipulation of thermochemical equations to do various things, and I'll talk to you about them. But this is just the list. So I'm going to read through these, and then we're going to go and give you examples of what these actually mean. We talked about this already. When an equation is reversed, the sign of the delta H, the enthalpy must be reversed. So in those diagrams, remember, if we're going from reactants to products, we can actually swap that. We can go from products to reactants, but we have to change the sign from a positive to a negative or a negative to positive. Next, if the coefficients and equations are multiplied or divided by the same factor, that enthalpy must also be multiplied or divided. So if we want, let's say we start in standard conditions where everything is 1 mole and we get out 100 kilojoules of energy. If we want 2 moles, we have to multiply that 100 kilojoules by 2, so we get 200 kilojoules of energy. So it's divided, it's the same amount, a ratio based off of the standard conditions. Finally, formulas can cancel from both sides. We've been practicing that, right, to make those net equations on if you set up chemical reactions over each other and use those arrows. If things are on the opposite sides of the arrows, they cancel out. If they're on the same side, you can add them up. And you also have to add up all of the delta H or enthalpy amounts for the chemical reaction. So let's do some practice problems here. Okay, so we have this compound, this chemical reaction, thermochemical reaction. What is the reverse reaction? So what if we take the products and we're going to make those reactants, and then we're going to create these as products instead of the reactant? So when we have the reverse reaction, what we have to do is we're going to write this out backwards. I'm going to take the Fe2O3 solid plus the 3CO gas. We're going to react to form 2 iron solid plus 3CO2 gas. And this is going to be the delta H value now is going to be a negative 26.7 kilojoules because we reversed the chemical reaction, so that has to be a negative value. Now we're asked for the reverse chemical reaction. What's the enthalpy change if you end up with 4 moles of solid iron? Well, here I have 2 moles of solid iron. I want 4, so I have to multiply this whole entire thing by 2, because 2 times 2 is equal to 4. So I'll have 2 iron 2 oxide plus 6 carbon monoxide. We'll react to form 4 iron solid groups, and then we'll get 6 carbon dioxide gas. This delta H, I'm going to take 26.7, multiply it by 2, and I get 53.4. Remember, that's a negative value because we reversed that chemical reaction above. So here we are with our final reaction, and we're able to determine that we should get an enthalpy change of negative 53.4 kilojoules. Now I'd like to look at adding these chemical reactions. And one of the first things, if we have, let's say we have 2 chemical reactions we want to add together to create a final chemical reaction. One of the things we have to do is we're going to generally be given what we want the end reaction to be. So here we know that we actually want to look at what would the chemical reaction for iron plus oxygen to make this iron 3 oxide solid compound. What would the change in energy be? And we're given these 2 different chemical reactions that we should be able to add together in order to get this. So the first thing that we want to do is we want to look at some of the compounds and where they are, if we need to reverse the chemical reaction or if it's fine in the forward direction. So here we know we have iron 3 oxide. So here is the iron 3. Remember, it's iron 3 because iron has a positive 3 charge. But this is on the right side. This product is on the right side, so it looks like we can use this chemical reaction. We're going to just leave this in the orientation it is without having to change anything. We know we have 2 elements of iron, 2 elements of iron. Now we have carbon dioxide. Carbon dioxide is not in this one. So we're going to need to get rid of this carbon dioxide component, and a way that we're going to be able to do that is by reversing this, flipping this carbon dioxide to the right side, and that then also gives us this oxygen compound on the left side. So let's do this. Let's take this first reaction, and we're going to just kind of write it out, and in the same order, in the same orientation. We're not multiplying it by anything. And this next one we're going to flip, but we also have to recognize that this first reaction has 3 carbon monoxide. This reaction has just a single carbon monoxide. So something else I'm going to be able to do so that I can cancel these units out on either side is I'm multiplying this whole thing by 3. So 3 times 1 is 3, and then we have 3 times 1 is 3, and then 3 times 1/2 is 3/2. So that gives me this new written out reaction. Now I can cancel out the similar units because I have 3 of each of these carbon monoxide groups on either side of this arrow. I can cancel out the carbon dioxide, so those go away now, and I have 2 iron elements. I have 3 halves oxygen, and I have 1 iron 3 oxide compound. So this now allows me to add my enthalpy groups together, because now I have the chemical reaction I'm looking for through a 2-step process. So I add these together, and I'm going to get negative 822.3 kilojoules. So this little bit of 26, right, is added into this big negative value. I get a slightly smaller negative value. So that's how we add these different groups together. That's one process. So remember, you want to get these elements on the proper side of your arrow. That's kind of step 1. Put these groups in so that you can get groups on the correct side. And then if you need to multiply the whole chemical reaction, notice this one, 3 halves, 3. The other thing that I did was I also, after I flipped it, I multiplied that negative 283 by 3, and that's what gave me a negative 849 here. So you'll have to do that in order to get your proper delta H value. So now I'd like you to try this. I want you to try to calculate the reaction for 2 carbon solid molecules plus H2 gas reacts to form C2H2 gas. Now you'll notice that these chemical reactions have all of these. I have C2H2 over here on the left side, that we're looking for that. The H2 is found in this third chemical reaction, and then the C, the solid carbon, is found in the middle reaction. So you're going to have to use all 3 of these chemical reactions. I would take a new piece of paper, write those out, manipulate these reactions, these thermochemical reactions, and their enthalpies, and then calculate the enthalpy for this reaction. So it should be one of these 5 different answers. Post your answer, and then tell me what you've done to these 3 equations. So basically just description. Did you multiply this one by 2, or did you reverse this one, or did you just leave this one alone? What did you actually do for these 3? And also the answer, and then post that on your Blackboard space, and we'll discuss. And that's the end of chapter 6. I recommend practicing a few more of these so you understand this process, and then we'll move on to the next chapters of looking more at chemical energy and different ways that molecules can have and possess and pass on energy through electromagnetic radiation.